Hello and welcome to another video in the Chemical Kinetics and Equilibrium discussion series. For this video, we will be discussing energy diagrams and reaction rates. For energy diagrams, on a molecular level, what happens when a reaction occurs? In order for two molecules to react, they must collide, and in the collision, the kinetic energy they possess is used to break bonds. So not every collision between molecules, however, leads to a reaction. Collisions must have the proper orientation and enough energy for the reaction to occur. So how does the orientation of a collision affect a reaction? Consider here a general reaction between two starting molecules, A, B, and C, in which the A bond is broken and a new bond between B and C is formed. So since C forms a new bond with B, a reaction occurs only when C collides with B. If C collides with A, no bond breaking or bond making can occur and the reaction does not take place. Since molecular collisions are random events, many collisions are ineffective because they do not place the reacting atoms to each other. So the energy of the reacting molecules also determines whether a particular collision will lead to a reaction. In any given sample, molecules possess a wide range of kinetic energies. Some are fast-moving and thus possess more kinetic energy than others that are slow-moving. Thus, any collisions that have sufficient energy and proper orientation lead to a reaction. So the energy changes in a reaction are often illustrated on an energy diagram, which plots energy on the vertical axis and the progress of the reaction or the reaction coordinate on the horizontal axis. The reactants are written on the left side and the products are on the right side. And a smooth curve that illustrates how energy changes with time connects them. Let's assume that the products here, A and BC, are lower in energy than the reactants A, B, and C. When the reactants A, B, and C approach each other, the electron clouds feel some repulsion, causing an increase in energy until a maximum value is reached. So this maximum value is this maximum value or the point wherein there is a maximum value is called the transition state. In the transition state, the bond between A and B is partially broken and the bond between B and C is partially formed. The transition state is located at the top of the energy hill that separates reactants from the products. So at the transition state, the bond between A and B can reform to regenerate reactants, or the bond between B and C can form to generate the products. As the bond forms between B and C, the energy decreases until some stable energy minimum is reached. The products are drawn lower in energy than the reactants to reflect the initial assumption about their relative energy. Remember that the E sub A, or the energy of activation, is the difference in energy between the reactants and the transition state. Now, the E sub A is also the minimum amount of energy that the reactants must possess for a reaction to occur. It is also called the energy barrier, and the height of the barrier determines the reaction rate. So the height of the energy barrier, or the magnitude of the energy of activation, determines the reaction rate or how fast the reaction occurs. We have to remember that when the energy of activation is high, few molecules have enough energy to cross the energy barrier and the reaction is slow. While if the energy of activation is low, many molecules have enough energy to cross the energy barrier and the reaction is fast. Now, for these energy diagrams, the difference in energy between the reactants and the products is the delta H that we have talked about in the previous video. We have to remember that if delta H is negative, the reaction is exothermic. So when the products are lower in energy than the reactant, as is the case here, the bonds in the product are stronger than the bonds in the reactant. Therefore, delta H is negative and the reaction is exothermic. Whereas, if delta H is positive, the reaction is endothermic. So energy diagrams can be drawn for any reaction, and in the endothermic reaction shown in this figure, the products are higher in energy than the reactants. An energy diagram is a visual tool that helps to illustrate both the rate of a reaction and the energy difference between the reactants and the products. Keep in mind that these two quantities are independent, and a large energy of activation does not tell us anything about the relative energies of the reactants and the products. So when we speak of reaction rates, as we learned in the previous slide, chemical reactions occur when molecules collide. So the rate of a reaction depends on the number of collisions and the effectiveness of each collisions. So how do these changes in concentration and temperature affect the reaction rate? For the first one, increasing the concentration of the reactants increases the number of collisions and increases the reaction rate as well. Now, when we increase the temperature of the reaction, it increases the kinetic energy of the molecule, and therefore it also increases the reaction rate. So increasing the temperature increases the reaction rate for two reasons. First, increasing the temperature increases the kinetic energy, which increases the number of collisions. Second, increasing the temperature increases the average kinetic energy of the reactants. Because the kinetic energy of colliding molecules is used for bond cleavage, more molecules have sufficient energy to cause bond breaking, and the reaction rate increases. As a general rule, a reaction rate doubles for each 10 degrees Celsius the temperature is raised. Similarly, a reaction rate is generally halved for each 10 degrees Celsius the temperature is lowered. Now, we frequently take advantage of the effect of temperature on reaction rate. We store food in a cold refrigerator to slow the reactions that causes the food to spoil. On the other hand, we use heat to bake bread to increase the rate of the reactions that occur during baking. In terms of the catalysts, some reactions do not occur in a reasonable period of time unless a catalyst is added. So when we say catalyst, it is a substance that speeds up the rate of a reaction. So a catalyst is recovered unchanged in a reaction and does not appear in the product. So they have no effect on the energies of the reactants and the products. Thus, the addition of a catalyst lowers the energy of activation but does not affect delta H. So, example, metals are often used as catalysts in reactions. In here, we have ethylene, and it does not react appreciably with hydrogen. Now, if we use palladium as our catalyst, a rapid reaction occurs and ethane is formed as the product. So, the metal serves as a surface that brings together both reactants, facilitating the reaction. So, catalysts accelerate a reaction by lowering the energy of activation without affecting delta H. So, here's an example or a diagram showing you that the uncatalyzed reaction has a higher energy activation, therefore making the reaction slower. Wherein the catalyzed reaction here has a lower energy activation. That's why the reaction is faster. But take note or keep in mind that the delta H is the same for both reactions. Now, if we look at the biological catalysts in our body, enzymes are biological catalysts held together in a very specific three-dimensional shape. So there is what we call the active site. I hope that this has been discussed in biology. So the active site binds a reactant which then undergoes a very specific reaction with an enhanced rate. The enzyme lactase, as an example, converts the carbohydrate lactose into two sugars which are glucose and galactose. So there are cases wherein people who lack adequate amounts of lactase suffer from abdominal cramping and diarrhea because they cannot digest lactose when it is ingested. So remember that the catalysts that synthesize and break down biological molecules in living organisms are governed by the same principles as the acids and metals in organic reactions. The catalysts in living organisms, however, are protein molecules which are called again enzymes. And that's the end of our discussion for the second video in the series. Thank you for listening.